Okay, welcome back to the summer school of research. Today we have a lecturer, Professor Kyoko Ishizaka. Let me briefly introduce her. She got a PhD degree in 2004 under the supervision of Professor Yoshi Tokura, and she spent 6 years at ISSP as a research associate with Professor Shin doing photo emission spectroscopy. And she then became associate professor in 2010 at the Department of Applied Physics. And then she got a co-assignment at Riken SEMS as a team leader. She started another lab at Riken from 2016. Then she became a full professor at the Quantum Phase Electronics Center of University of Tokyo, where I'm also belonging. And she's one of the youngest professor in the department, very active in photoelectron spectroscopy. And she will tell us on materials science driven by laser photoelectrons. Professor Ishizaka, please go ahead. But wait a minute. So for the audience, if you have a question, you can use the chat function. You can just type your question, and the Professor Ishizaka can see it. And if she or I decide it's better to reply now, answer to this question now, she can interrupt and she can reply to the question, or later on, 75 minutes lecture, I can name you, and you can unmute and you can shout your question. So either way, anyway, so don't unmute before I ask. So if you have a question, please type your question in the chat function. All right? Okay, Professor Ishizaka, please go ahead.
Okay, thank you so much, Kawasaki-sensei, for the kind introduction. So my name is Kyoko Ishizaka. I'm connected from Tokyo. So first, I'd like to thank all the organizing professors for giving me a chance to give this seminar in this summer school. And it's a really pity that I really wanted to visit this Light-induced summer school, but well, we have to stay at our own place. And I hope all of you are staying well and healthy at your own places. So today I'd like to talk about this topic, the material science driven by laser photoelectrons. So I wondered a little bit about what to talk about, but I decided to kind of focus on this rather recent topic about our approach on how to detect out of equilibrium states in matters. So, okay, let me start. So the outline of my talk will be like this. So for the first part, I'd like to briefly introduce my activities, recent kind of 10 years activities. And then the main part of my talk will be these two. So one is the ultra-fast nematic excitation we observed in the superconductor iron selenide. We used the time-resolved ARPES for this topic. The second half is a kind of more recent topic we are working on. We are kind of developing the ultra-fast electron microscope, and we recently working on this phonon imaging by using this probe. So I'd like to introduce our recent result. And last, I'd like to summarize. And if I have time, I'd like to speak about some perspectives. So let me start. So this slide is the very introductory part. So as I think many of you know, the photoelectric effect is a kind of a very old-fashioned story, first discovered by Hertz in 1880s. So he found the photoelectric effect, and then Einstein gave some explanation about this phenomena by introducing the light quantum hypothesis. Then he found its quantum effect. And after that, the Millikan, he confirmed experimentally that there is energy conservation law holding in this photoelectric effect. So what we know about these people's work is that photons, when we irradiate some material by high energy photons, electrons come out. So there's a one-by-one correspondence between these irradiated photons and the photoelectrons. So the photoelectrons can be used so for example, to probe some electrons inside the materials. So by using these photoelectrons, we are recently working on this kind of probes. So I think many of you know about this angle resolved photoemission spectroscopy. I think there was already some lecture by Professor Kleisen. And so the ARPES can resolve the electronic states into energy, momentum, spins. And recently we are trying to push this towards this time resolved and also microscope, so that we can detect electronic structures into many informations. So actually, most of my, for example, publication list is composed of this ARPES works, but more recently, we are kind of working on this new probes, which uses the ultra-fast part of the lasers. So by using the ultra-fast lasers and combining it with these electron sources, we can create the electron pulse, and then we can perform kind of a pump probe type ultra-fast measurements by using these electron beams. And these are the more new techniques we are working on. So we are working on the ultra-fast electron diffraction and ultra-fast electron microscope, which can probe these ultra-fast electron lattice and nematic states informations. And today, I would like to talk about this time-resolved ARPES for the first topic. And for the second topic, I'd like to talk about this ultra-fast TM. Okay, so let me start from the ARPES. So I think many of you already know about ARPES. So what is ARPES? So from ARPES, we can measure this energy and crystal momentum and angular momentum of the electrons. So by using this conservation laws on energy, momentum, and angular momentum, we can obtain this energy and momentum. And if you do spin resolved measurement, we can also measure the spins in the occupied states. So this is a very important information for the solid state physics, because in these periodic systems, the crystal momentum K is a very, very important parameter. So by using this ARPES, we can resolve the electronic states into this momentum, Kx, Ky, energy, and spins. So this is just example we got in this material, plasma bismuth 2. We get this data cone type dispersion with these down and up spins like this. So this is the ARPES. And what we can further obtain by this photoelectron spectroscopy is that if we look into the detail, besides these valence band structures, Fermi surface, we can also look at these orbital characters of these wave functions composing the Fermi surfaces and bands. And also, if we have a good enough energy resolution, we can also look into the gaps, like superconducting gaps. This is the superconducting gap spectrum in this osmium pyrocore system. At high temperature, it shows usual Fermi Dirac-like distribution at the Fermi level because it's a metal. But when you cool it down below the transition temperature, this nice superconducting peak appears, and we can estimate the gap from this spectrum like this. And also, for example, in the strongly correlated system, in some case like Wiltonate, we can observe this kind of condor resonance type peaks appearing near the Fermi level like this. So we can get many informations by using the photoelectron spectroscopy. Okay. So I think there are many people working on this photoelectron spectroscopy, but we've been kind of focusing on the laser as a light source for this photoelectron spectroscopy. So in the conventional system, many people use this helium discharge lamp, which is commercially available, and it's very easy to use. But when you use this kind of a discharge lamp, the energy resolution is limited, and also as a light, it's very incoherent, and we cannot get a nice polarization, and also we cannot make the small spot size. So it's a little bit difficult to control into this coherent. Compared to the coherent light, it's a little bit difficult to use. So, but when we use a laser, we can get many new merits. So if we can get polarization, for example, and with this polarization, we can discuss the parity and dichroism of these wave functions. And and also if we use a short pulse laser, there's a Heisenberg uncertainty rule between this energy width, delta E, and the pulse duration, the time width, delta tau. There's this rule. Okay, so if you make the pulse duration very long, very long, you can get a nice narrow energy vision. But when you go to the short pulse, like below 100 femtoseconds, the energy becomes broader because of this uncertainty rule. So, but in other words, if we use the long pulse laser, we can get a very high energy resolution for this ARPES measurement. Okay, and if you use the short pulse laser, we can not get a nice energy resolution, but then we can get the time information by doing the time result measurement. So both are very important, and in these 10 years, I have been rather worked on this high energy resolution measurement by using these lasers. And so with maybe 2 or 3 minutes, let me quickly introduce what kind of experiments I have been working with this high energy resolution side. Okay. So this is a schematic of our system in the laboratory. And by using this VUV 5 to 6 CV laser, we can get a very nice energy resolution. It is below 0.6 millieV, which is very good. And also we can get a very nice small spot size. Now it's around 15 micron or so. So we can selectively measure the small samples. So this is one we use with this long pulse laser. And this is just a kind of advertisement, okay? So with this, we are now working on this kind of microflake samples with like a 10, 20 micrometer size. We can successfully measure these band dispersions by selecting this part here by using this laser system. So it's a very useful system as a for the high energy resolution measurement. Okay. And let me quickly go through these materials we've been working. So in this 10 years, we've been working on, for example, rush bar type semiconductor with this large spin splitting. This is a spin down and spin up. Okay. And also the spin barrier semiconductor with a spin up, down, which is coupled to this momentum. Okay. And recently we also worked on this chiral type semiconductor, which is a tellurium. So in this case, there is a spin polarization, which is coupled to the right-handed crystal and the left-handed crystal. The spin reverses when we change the, when we look at the different chirality of the crystals. Okay? And there are many other topological materials we've been working on. And this is recently, we also worked on some CDW charge density wave materials. And once we switched on the charge density wave, the topological surface state disappears. And this CDW transition induces a topological transition. So by utilizing this ARPES, we can find many interesting materials like this. Okay. Oh, sorry. And also, this is also some summarize. But we've been also working on these iron-based superconductors. So maybe you already heard in some lecture, but in iron-based superconductors, there are many new states, quantum states appearing. For example, there's a ferro-orbital nematic order appearing as this different energy between these dxz and dyz orbitals. And also we get many kind of unusual phase diagrams, like multiple sugar gaps and some hidden antiferric electron structures appearing in this anomalous normal state. So I don't go into detail, but ARPES can measure this kind of superconducting state and anomalous normal state and these electric bands in these many strongly correlated systems. So okay, and so today I'd like to rather focus on this time resolved measurement. So okay, by using the short pulse laser, we can go into the non-equilibrium state by performing the time resolved measurement. So let me introduce the more recent works we've been working. So this is a time resolved ARPES system. I'll come back to this after in the main topic. But by using the lasers and short pulse lasers, we can measure these electronic structures, energy, momentum, and time in this 250 femtosecond time resolution. Okay, so by using this, we can measure this how the electronic structures are modified as a function of time. Okay, and okay, so this is the one I will talk about in the second topic. But by combining this femtosecond laser with this electron probes, electron guns, we can create the electron pulses by generated by the UV laser pulse at the photocathode. And then with this, we can measure this nanoscale imaging and Lorentz imaging, diffraction, and many things. And I'll come back to this in the second topic. So in this part, I just try to briefly show what kind of works we've been working. But today, I will talk about this topic and this topic. Okay, so let me move on to this main part. So for the first part, I would like to talk about this ultra-fast nematic excitation we found in the superconductor iron selenide. So let me start with what is a nematicity in this case, and how we detected the energy, momentum, and orbital by this time resolved ARPES. And let me show what kind of phenomena we've found, which is the collective excitation of this Fermi surface. Okay. Okay, so let me start is this, what is the nematicity in quantum materials? So the nematicity is a word from the classical liquid crystals field. So in the case of the classical liquid crystals, the direction of this liquid crystal is brought by these rod-like molecules. So there are the clouds of the molecules, rod-like molecules like this. And in the nematic phase, the direction of the molecules are aligned along one direction, which is characterized by the director here. So in this case, the rotational symmetry is broken like this. And in the case of synectic phase, in addition to the rotational symmetries broken, there's also some translational symmetries broken. So this is a synectic phase in the classical liquid crystals. And there are many patterns of the liquid crystals. So, but in the case of the cholesteric case, there is a chirality shows up, and this the direction of the molecules. The direction of the molecules shows up as a right-handed and left-handed chirality like this. So in the case of the classical case, classical liquid crystals, the rod-like molecules, the direction of the rod determines the character of these liquid crystals. So, but in 1998, Professor Kiberson, Fradkin, and Emery introduced some liquid crystals into this electronic state. So in the case of electronic state, electron systems, the electron is just a point-like particle, so it doesn't have any directions. So at the first glance, nobody expects any things like liquid crystals from these electrons, but they introduce some mesoscopic patterns generated by these electrons, and in some cases, they show that this kind of liquid crystal phase can appear in these electron systems. So in case of nematic system, there is a kind of these electron stripes running along one direction. And in the synectic case, it's more like a ordered kind of stripe. And in case of isotropic, it shows up like this. So they started to discuss this kind of electronic liquid crystals in relation to these high tissue cuprates. So maybe many of you know, I don't know, but it's so famous that in the high tissue cuprates, there is a so-called stripe instability. So the doped holes tend to form the stripe, and it fluctuates like this. So it could be characterized by this nematic or synthetic liquid crystals. So from this time, we started thinking about these liquid crystals that can occur in these solid state electron systems arising from this strong correlation. Okay, and since after that, we now have many examples of these quantum liquid crystals appearing in many systems. So this the left-hand side. This is the one scenario I just showed you in the previous slide. But after that, there's another mechanism suggested that can generate the nematic phase in the electronic systems, which is the Pomeranchuk instability. So in the usual Fermi liquid, the electron system is, of course, it's isotropic. But when there is a Pomeranchuk instability, these electron systems lose the rotational symmetry, and it becomes two-fold symmetric like this. So in either case, the electron correlation is a very important pair. Okay, so maybe I should not go into the detail, but just as I showed you in the previous slide, there is a high tissue cuprates which shows a stripe instability like this, and also in the more kind of a simple system to the electron gas system. When the high magnetic field is applied, there's anisotropic electron states appearing like this. And also it is a very strongly correlated system, strontium glutamate oxide. Also it shows some anisotropic electronic state when magnetic field is applied like this. And this one, iron-based superconductor, this is one I will talk about. Okay, but more recently, like in these 3-4 years, there are many other examples coming up as nematic quantum nematic state, like a topological superconductivity and also heavy fermion superconductors. So as you can see in these recent materials, the superconductors are kind of seemingly have some relation with these nematic phases. It's very interesting, and this is just a really advertisement, but we have just started a big project on these quantum liquid crystals. And so there are many groups, but I belong to this group. So in this group, I will try to control the quantum liquid crystal and make some functions out of that. Okay, so there are this kind of big projects to investigate these quantum liquid crystals. Okay, but from now on, let me focus on these iron-based superconductors. Okay, so in these iron-based superconductors, this nematic states appears very ubiquitously. So there are many families of these iron superconductors, but in most of these systems, this nematic state appears in this region of this phase diagram. So, okay. So these systems, these iron-based superconductor systems, they, as a crystal structure, they have a tetragonal crystal structure, but as it's good. Oh, sorry, I noticed the chat, but what else as well? Can I answer to this question now? Okay.
What's the problem?
I just found the question in the chat. Can I answer this question right now?
Yeah.
Okay. Okay, so, okay. Maybe all of you are seeing this chat question, I guess. What acts as a rod in these quantum liquid crystals? Okay, this is a very important question, and there's no rod in these quantum liquid crystals. That's very important aspect. So maybe I shouldn't take too much time here, but okay. So in the classical case, the molecule itself has a rod, but in these systems, this particle itself doesn't have any directions. So it's completely different from these classical liquid crystals. So it is a very important and difficult question, but I guess it's what plays a very important role here in this quantum liquid crystal is the correlation, strong correlation among these electrons, and in some cases also spin or orbital degrees of freedom. But I think this question is the main point of this project itself. Okay. Okay, so if it's okay, let me go on. So this is a phase diagram, and yeah, maybe I already explained. So at high temperature, everything is a four-fold symmetric, but when you go down to the low temperature, many things becomes two-fold symmetric, like an antiferromagnetic state, and also many other two-fold characters appear. Let me just, okay, here. So this is antiferromagnetic order, which is a two-fold symmetric magnetic state, okay? And here the superconductivity appears, but here, when you go down across this temperature, the crystal structure also goes from tetragonal to orthorhombic. So it goes to the C4 to the C2 state. And of course, it's very coupled to each other, but also there is a XZ and YZ orbital order. So in the four-fold symmetric case, this YZ and XZ should be completely degenerate. But when you go down, cool this system down below this temperature, the energy level between this XZ and YZ becomes non-equivalent. That's what we call the orbital order. So, okay. in the iron-based superconductors, many things happens, and at low temperatures, the system becomes two-fold symmetric. Okay. Oh, sorry, and also at high temperatures, the fluctuation of these two-fold symmetric signatures remains to high temperatures, and sometimes it's called nematic fluctuations, and it appears in this anisotropic resistivity. Okay. So, so there are many discussions on this nematic state, but as I already stated, there are too many players involved in this nematic order. So one is lattice orthorhombic from tetragon to orthorhombic, and spin nematicity, which also coupled to this antiferromagnetic phase. And as I already told you, there's orbital order, Xg and Yg. So orbital and spin and lattice, there are many players, and as you can see in this title of this paper, it's very difficult to say who is driving this nematic order, okay? Because these transitions occurs almost at the same time when you cool the temperature. So who drives who is very difficult to program, okay? So, okay, but so we are kind of interested in this nematic phase appearing in this iron-based superconductors. And we particularly selected this system, iron selenide. There are many reasons, but because it has a simple crystal structure, but what is very important is that it shows the tetragon to orthorhombic nematic lattice transition at 19 Kelvin, but no magnetic order in these systems. So it's quite simple. So there are orbital spin and lattice players, but in this system, at least the magnetics, the spins are kind of it doesn't show up as the magnetic order in this case. So we can rather concentrate on these lattice and orbitals. Okay. So that's why we chose these systems to study the nematic state into the detail. So this is a resistivity and this lattice constant. So there's also orthorhombic state shows up at 90 Kelvin. And for the nematic fluctuations, there's a very nice electronic Raman scattering studies are done. And they can, the electron Raman scattering can derive some physical quantity corresponding to the nematic susceptibility. And they derive the nematic susceptibility, and they find that it's enhancing toward this transition temperature, and there's a peak like this. So there are many studies on these nematic fluctuations and nematic transitions in this material. Okay. So, okay. So by usual ARPES, static ARPES, we first in this 2014-15, we try to clarify the nematic state in this iron selenide, and we find that at high temperature, it's for the symmetric Fermi surface like this. But when you cool down below the nematic phase transition, the Fermi surface changes into this elliptical shape. Okay, so it reminds us of this. Okay, so this circular to the elliptical shape. So it reminds us of this Pomeranchuk instability scenario like this. Okay, so we found this nematic state in 2014-15, and then we wanted to okay, look at what kind of okay, so this is a Fermi surface at high temperature, and this is a Fermi surface at low temperature. But when you look at the band dispersion, you can say that the band dispersion along the kx direction, like this. So there's a YZ orbital crossing the Fermi level, and along the ky direction, this xz orbital crossing the Fermi level. But as you can see, it's four-fold symmetric, like this. But when you go down to the orthorhombic phase, you can see that this along this short axis, the Fermi surface is composed of this YZ and XZ mixed state. But along this KY long axis state, you can see that XZ orbital is composing this Fermi surface. And the Fermi momentum becomes very different along KX and KY. So this is what's happening in this nematic state. Okay, and we passed our result to the theorist, and they try to reproduce our ARPES result by doing the tight bind model. And then they find that when they introduce the orbital order of this 10 millieV between this XZ and YZ, then they can kind of nicely reproduce our ARPES result. So, okay, so this is the result of the usual static ARPES experiment. So we find that from this experiment, we found that in the nematic state, there is a 10 millieV energy difference between this XZ and YZ order. Okay. So this is the work in 2015, and then and this is a motivation of today's talk. Okay, so it's okay. We found some the electronic structure in the nematic phase like this. There's an orbital order between XZ and YZ, and the Fermi surface becomes circular, from circular to the elliptical phase. So that's okay with the nematic phase. But as usually when there is a symmetry breaking induced, there is a corrective excitation appears to recover the broken symmetry. So in the case of CDW system, it breaks the translational symmetry. So to try to recover this translational symmetry, there is a phonons or coherent phonons, phonons, amplitudes and phasons appearing in this CDW state. So it appears in this time domain measurement. Okay. In case of magnets, there's a time reversal symmetry broken. So to recover this symmetry, there's a magnon or spin wave appearing in these magnets. So what about the nematic state? So the rotational symmetry is broken. So there could be some excitation to recover this rotational symmetry. Okay. So in this case, we already observed that there's a rotational symmetry breaking in this Fermi surface, and also we found some orbital order in the XZ and YZ component. So our motivation on working on this system is to investigate the collective excitations and dynamics that could be peculiar to this nematic state. Okay, and also in the case of ion-based superconductors, we have to always care about this who is the driver. So in this case, ion selenide, what is electron, which drives this phase transition or this nematic state. So that's our motivation on this work. Okay. So this is a schematic of our time-resolved ARPES work. So we first prepared this ion selenide sample, and we tried to apply the strain to one direction and to between to make the single domain orthorhombic sample like this. And then we bring this to the time-resolved ARPES system. So by using this pump probe, which is a 1.5 eV red laser, it can excite this system here in this sample. And then we use this ultraviolet pulse to probe this system via the photoelectric effect. And by detecting these photoelectrons, we can measure the electron structures just after this pump, which excites the system. So by changing the timing of this delay timing, we can measure this the series of these stroboscopic picture of the electron structures. And this is a kind of a result I already showed here. But with this measurement, we observed this very ultra-fast change of the Fermi surface shape and also the oscillation of the Fermi surface. And today I didn't bring this part, but we also successfully observed the orbital components changing from YZ to XZ and then YZ. So all these kind of oscillation occurs in this time scale of the 1 picosecond. So from this, from the next slide, I would like to show you the result. Okay. Sorry, so this is a setup of the experiment. So I just as I showed you, this is a pump here and a VLB probe pulse here, but we make these pulses from the single laser like this. We separate the beam into two, and we make the false harmonic generation for one of the beam and make the VLB ultraviolet pump. Ultraviolet probe pulse like this. And by changing this length of this delay stage, we can change the timing between this pump pulse and probe pulse. And so the time resolution of this measurement is around 250 femtoseconds, and the energy resolution is around 12 millieV, which is almost in the Heisenberg's relationship. Okay. So from the next slide, I would like to show you the result. So I'm not sure if this, what is actually the retraining device. Okay. Let me answer your question also here. So this is a retraining device, the picture of the retraining device. So this part is ion selenide sample, which is a very thin, how thin, maybe like a 500 micron thickness or so. So this is a very thin sample, and we stick this sample by some paste. So left hand side is sticked in this block, and the right hand side is sticked on this part. And there's a screw, it's cut, but by rotating this screw, we can either, how to say, push the sample to this direction or pull this sample to this direction. So in this case, we rotate the screw to pull this flake sample along this direction. Okay. So if you do it too much, of course it's breaks. So it's quite a difficult measurement, but in like this, so you just apply the strain by rotating the screw under this bridge. Okay. So this is the movie, and I'm not sure if it will move properly. Yeah, on my display it's moved properly, but let me do it again. So, okay, first let me explain. So this is the band dispersion along the short axis, and this is a band dispersion along the long axis. And this black curve is the cut profile along this line. So the peak of this black curve is a Fermi momentum, okay? So along the long axis, the Fermi momentum is around 0.08, and along the short axis, the Fermi momentum is around 0.06 or something. And please try to look at this peak position, okay? It will move again like this. So I don't know if it's moving, but okay, so let me pick up the two images as 2 times. So this is the image before pumping. So it's the kind of ground state. So at the first time, this kfx and kfy, the short kf and long kf is quite different. But this is 120 femtosecond, which is just at the pumping. So just at the pumping, it becomes equivalent. And it means that the Fermi surface becomes completely circular when it's pumped, okay? So I don't know if it's worked very well, but this movie shows that this elliptical Fermi surface first goes to the circular, and then it moves back to the elliptical shape again, okay? And this is the change of the Fermi momentum as a function of this pump fluence. So when you excite the system stronger and stronger, this change of the Fermi momentum increases like this. But at some point, it saturates. It means that the Fermi surface just after pumping becomes completely circular along this region. So in this region, this is a weak excitation regime. So which means that the Fermi surface only partly becomes circular. But in this strong excitation regime, the Fermi surface completely becomes circular and four-fold symmetric. Okay. And okay, and in this strongly excited regime, we can measure the electronic temperature by measuring this Fermi Dirac, the Fermi edge at the Fermi level, and by fitting the Fermi edge by the Fermi Dirac function, we can get the electronic temperature, and we can see that at this strong excited regime, the electron temperature reaches 90 Kelvin, which is a transition temperature in the equilibrium state. So when you pump excited system above this fluence, we can achieve the very high, the high temperature phase, which is the high electron temperature phase. Okay. And this is the time-dependent curve of the Fermi momentum. So when weakly excited, the Fermi momentum changes a little bit and recovers. And when you increase this exciting fluence power, then this change becomes larger and larger. And at some point, it starts to oscillate like this. Okay. And when you go to the more stronger region, the change of the Fermi momentum saturates, but it's a little bit hard to see, but maybe you can see that there's a small oscillation components here. Okay. So we try to extract these oscillation components and try to figure out what's happening. Okay, so this curve is this one, the one at the 220 fluence here. So here we can clearly see that this Fermi momentum first, in the case of the longer Fermi momentum, it first decreases and it starts oscillation and recovers. And for the shorter Fermi momentum, it becomes longer and then it also shows a slight oscillation. And we try to extract this oscillation part by fitting with this function. So this first term is a usual exponential relaxation like this here. And the second term is a very long term, so this tail like this. So you can forget about this second term right now. It's longer than ATP per second, but you can just forget about it. And for the third term is this oscillation term, okay? So for the first term, it shows that this circular Fermi surface goes back to the elliptical shape in 850 femtosecond like this, okay? And on its way back to this recovery process, there is oscillation with this time period of 1.4 picosecond and the lifetime is about 500 femtoseconds. Okay, I hope. Okay, so yeah, by doing this fitting, we can derive this relaxation time here, 850 femtoseconds, and this oscillation time here with 1.4 picosecond time period. And from this short axis Fermi momentum and the long axis Fermi momentum, we made a schematic Fermi surface as a function of time. And I hope it moves well. Okay. I'm not sure if it's working well, but I hope you can see this Fermi surface going to the circular shape, and it's way going back to the elliptic shape. It has some small oscillation. And to show it more clearly, it's not a very correct thing to do, but we try to show it by exaggerating this third term by multiplying by 3 times. And then the dynamics looks up like this. Okay, so that's what's happening. So when you hit this system by the pump light, the two-hole Fermi surface becomes circular, and then it shows like this kind of breathing-like oscillation and go back to the elliptical shape. Okay. So maybe I should skip the detail here, but the similar analysis can be done for each pump fluence. And okay, sorry, let me skip. So as a function of pump fluence, we can get that there is a very unusual behavior as a function of the fluence. That's this, when you go to the strong excited regime, everything becomes faster. The oscillation becomes faster, and the relaxation time also becomes faster. So there's some kind of a critical fluctuation appearing here. Okay, so this is a schematic. So when you hit this system and when you break this nematic state, then this kind of oscillation appears. Very short life oscillation appears in this region. That's what we found from this time resolved ARPES measurement. So by measuring the momentum and energy in this time, we can find this kind of short life corrective excitation. And okay, okay. Maybe I'm running out of time, so let me summarize this part. So what we found is a short life corrective excitation in the time domain, which appears as this Fermi surface oscillation. Okay, and so since it appears in a very quick response, we can conclude that this nematic change is driven by the electron, not the phonon. Okay. Okay. And as a perspective, we are kind of very interested in this collective nematic excitation in relation to this superconductivity. So at present, we only observe this nematic excitation in the normal state, but it could be closely related with the superconductivity. So we want to measure this these kind of oscillation, corrective oscillation in the superconducting state. We are now trying to do it in the low temperature. And if it's closely related, maybe we can control the superconducting state by using this nematic excitation in future sometimes. Okay, and in a more general aspect, maybe we also we want to find out the relationship between this collective nematic excitation and the quantum critical point. So when you lower the transition temperature into the zero temperature, maybe this nematic excitation can enhance, or yeah, and maybe it can show different kind of behavior. So as a perspective, we are working on this kind of works right now, and also in other systems. Okay, so in the remaining time, I'd like to talk about the second topic. Okay, so the second topic is for the second topic, we are using this ultra-fast transmission electron microscopy. We started working like 2 years ago or something like that. And also, I already stated in the introduction part, by using the femtosecond laser or nanosecond laser, whatever, the pulse laser, with this electron gun, we can generate these electron pulses, and we can measure many things in nanoscales. So this ultra-fast TEM is now being developed by this Dr. Takahiro Shimojima and Dr. Asuka Nakamura in Weekend. Okay. And our motivation of developing this ultra-fast TEM is like this. So by using the TEM, we can measure many things. For example, by using the bright field or dark field imaging, we can measure many nanometric motions of these materials. And by using the Williams mode, we can also measure the magnetic contrast. So this is skermions in this ion germanium. These particles are the skermions. And by using the electron diffraction, and this is a pattern of the convergent beam electron diffraction, but by using this diffraction, we can also get information of the crystal lattice, local crystal lattice here. And for this part, we are not yet working on, but by using the electron energy loss spectroscopy method, we can also get some information of these electronic excitations inside the material. And in some cases, we can also map out image the near field electric field distribution during this optical irradiation. Okay, so we can get many information in this picosecond and nanometer scales if we use this kind of ultra-fast TEM. And just let me skip this specification performance, but let me skip. So the first, we started with this phononic phenomena that can be observed by this ultra-fast TEM. So when you, in general, when you irradiate some short pulse laser onto some material, what happens first is optical transition of the electrons. And then the electrons' energies are the transferred with each other, and the electron simulation occurs in femtosecond scales. And then by the electron phonon coupling, the lattice starts to heat up, and then it diffuses as a heat in the sample in this time scale. And when you look at the phononic phenomena, there are many. There are many phononic phenomena occurring in this time scale. So first, of course, the atomic motion occurs, and the coherent phonons, or in some cases shock waves, and in some cases phase transition occurs. And then a more longer time scale, the expansion or mechanical vibration starts. So there are many phononic phenomena triggered by this optical irradiation. And of course, there's a big field of the phononic field, but we are trying to combine the material science with this phononic field. Okay. And the first one we tried is this vanadium ditelluride, which is one of the transition metal dicalcogenide. And it shows a charge density wave. At high temperature, it's uniform trigonal state, but when you cool down this compound below 480 Kelvin, it shows this kind of a zigzag type charge density wave. Okay. And there's a huge bond shrinks, like 8% of this lattice constant. And from the chemistry viewpoint, it can be regarded as this trimer bonding between this vanadium, like this. So it's a very unique CDW system with a huge lattice distortion. And this is, okay, this is a side way, but we also measured the ARPES in this material, and we found a very big change in the electronic structures like this. Some bands shows very flat bands, which corresponds to the trimers, vanadium trimers, and then this topological surface states completely disappears like this. So it's another story, but from this we can say that this CDW state is strongly coupled to the electron structure and gives us the chance that we can control this CDW state by using light. Okay. So our first idea was to break the CDW by the optical path and derive some structural instability. So in the usual case, when you irradiate the photons, optical pulses onto the samples, it usually shows a thermal expansion, and the phononic vibration is almost dominated by the longitudinal displacements. But if you use this sample, maybe some other kind of the displacement could be triggered. So our target was to first break the CDW by the light, and then try to see what kind of phonons or strains or structural dynamics can be triggered by this CDW. Okay, so let me start. Oh, sorry. So this is a diffraction pattern obtained by the TM. So, okay, so there's many black peaks around here. And when you look at the CDW superlattice peak, you can see that when we hit the sample by the light, it decreases like this. So we can see that CDW is broken to some extent just after the optical excitation. But this black peak rather changes very slowly and increases like this. So we go on to the longer time scale, and it looks like this. Okay, so the CDW first breaks like this, but the other black peaks shows a very long time oscillations, like 100 picosecond or 50 picosecond. So, okay, like this. Okay, and what T is the sample before? Oh, it's a nice question. It's 300 Kelvin room temperature. So it's in the low temperature phase, okay. CDW phase. Okay, and so this is, so what is this oscillation? I will talk about that. And okay, we first calculated the sound velocity, and then we find out that this slower oscillations corresponds to the transverse acoustic phonon, and this faster oscillation corresponds to the longitudinal acoustic phonon. So from this time period and this thickness of this sample, we can estimate the sound velocity like this. So the this strain pulse traveling back and forth along this sample thickness, and it appears as this oscillation. So we can estimate the sound velocity from the experiments, and we compared it with the calculation, and we found a very nice agreement like this. So from this comparison, we can say that this is the transverse acoustic phonon, and this is a longitudinal acoustic phonon. And as I first mentioned, this transverse acoustic phonon is very rare, and it usually doesn't appear in the usual material. But in this case, there's a big transverse acoustic phonon. Okay, So when we write down in the schematic picture, it looks like this. So it is a CDW melting, and this is a transverse phonon like this, and this is a longitudinal phonon like this. And we also measured the its dependence on this pump fluence, and we see that when you excite the sample stronger and stronger, there's a threshold behavior in the CDW and also in the transverse acoustic phonon. So we can say that this transverse acoustic phonon is triggered by CDW, but this longitudinal acoustic phonon is rather not affected by the CDW, which means it's generated by the usual photothermal mechanism. So this TA phonon is very unusual in this case. And we also measured, tried to image how these phonons travel along this thin flake. So I'm not sure if it moves properly, but okay. If this is, I'm not sure if it's appearing well, but if it's correctly appeared in your display, there's a wave source around here, and there's a these kind of waves propagating along these directions. So when you cut, for example, along here, this is the x-axis, and try to show this contrast change along across as a function of the time. It appears like this. So along this direction, these waves are traveling like this as a function of time. So when you okay, as a time passes by, this wave front moves from this here to here in along x direction. So from this gradient, you can estimate the sound velocity along this direction, okay? And for this y direction, we also do the similar thing. And then we can also estimate the sound velocity along this y direction. And we find that there is a significant difference between this x direction and y direction. So along x direction, there's a sound velocity was around 4 kilometers per second, but along y second, it's like 2.8, which is quite different. And I don't go into the detail, but by doing the calculation, sound wave calculation inside this thin plate, we find a nice agreement. And what we can conclude from this is that the phonon dynamics or strain dynamics in this material is very unusual or irregular. So everything is triggered by CDW mating. So the very first time the CDW gets broken by the optical pulse, and then it generates this kind of a transverse phonon along this thickness direction, and then it travels along the sample, thin flake sample. And these phonons, all of them are carrying this polarization along X, which is along this direction, coupled to the CDW. So our conclusion is by using this CDW material, we can kind of generate this unusually polarized phonons. That is our conclusion. Okay, and the second conclusion is that we can kind of observe or unveil this spatial temporal structure of this phonon dynamics from 1 picosecond to nanosecond or microsecond, and from around several nanometer to this micrometer scale. Okay. And this is, I guess, the last slide. So I'm not sure if it moves, but can you see this is a nanosecond time scale? So it's a longer time scale. So this is a kind of summarize of this phonon dynamics in this material. So in the very first time stage, there's a CDW CW dissolution occurs, and then some phonons, acoustic phonons appears. But when you go to the more and more slower, like nanoseconds, microsecond time regime, there's always some kind of oscillations in their time scales. So it shows how these phonons, local phonons, propagate into this kind of global mechanical oscillations. It's 2 picoseconds to 70 picoseconds, 20 nanoseconds, 2 microseconds. So it eventually goes into this global drumming-like nanoscale mechanical oscillations. So these kind of phenomena can be imaged by using this ultrafast TM. So, so this is almost a summary of my talk. And this is a perspective. We are also now trying to measure this nanoscale magnetic contrast, like skyrmions and magnetic domains. And at present, we are mostly working on the optical excitation, but we are also trying to excite the system by using the electric current path. And yeah, from now on, we are trying to visualize the excited states in many condensed materials and try to coherently manipulate the state of matters, quantum state of matters, and try to derive some new functions. Okay, so I think the time is almost up, and okay, so this is the collaborators. So the first part of my talk, time resolved ARPES, have been done by Shimojima-san and Suzuki-san, and ultrafast TEM development experiments also done by Shimojima-san and Nakamura-san. And we are collaborating a lot with many people. And for the time resolved ARPES, we are collaborating with Professor Shin in ISSB. And the samples are coming from Kyoto University. And for the last half, it's Osaka University. And also theories. And also we had a very nice discussion with Professor Paul and Gare in Paris. And so thank you for the collaboration. And yeah, I'd like to finish this my talk. And thank you very much for your kind attention.
Thank you very much. Okay, this lecture is open for question. If some of you want to ask question, please unmute your microphone and shout. By the way, Ishizaka-san, did you reply to the question from Ingrid Zimmerman?
Yes, yeah, I think so. I hope so. I think so.
Okay,
yeah.
great.
Yeah.
Right. So if you are shy, just you can repeat.
Can I?
Yeah,
can I ask? Hi. So thank you for the lecture. So I have a few questions regarding the first part. So you showed this nice video of when you pump the system, the Fermi surface becomes isotropic and then back to its extended phase. Do you claim that the system loses its tetragonal phase when you pump it with light?
It's a very nice question. You mean the lattice structure, crystal lattice structure?
Yes.
So my answer is no. The lattice remains orthorhombic, and actually we didn't do that experiment by ourselves, but there are some people working on this time resolved XRD, X-ray diffraction, and according to their result, the orthorhombic lattice becomes or not become, but the approaches at the tetragonal phase in a much slower time scale, like 30 picosecond or so. I think
If for example, you just
Yes.
take this crystal and continuously shine it with light, and then do some experiments, does the phase transition signature still remain? Let's say you cool it and you look for, you showed, I think, for the same material, where you cool it down, you measure its resistivity, and you show this feature at the phase transition. So if I continuously shine it with light, will I still have this feature?
Well, it's a difficult problem. At present I don't think so. At present I don't think so.
Okay.
So
Yeah.
so this is okay. This is XRD in a different system, but the time scale is 35 picoseconds. So the lattice structure itself responds more slowly. Okay, that's one thing. And your second question is that if you keep shining the light, you want, if this, okay, if you keep the if you keep shining the light, does the transition occurs? Right? That is the second question. Right?
Yeah, it's just because it really looks like it's becoming isotropic, so it really looks like it changes the phase. But I don't know, maybe I'm misinterpreting it, and
Yeah,
it's
yeah,
just
it's a very
some fluctuation.
good question. Yeah, so so at present in our result, so this isotropic phase disappears or recovers in less than 1 picosecond. Okay, so it's a very short lifetime state. Okay, so if you want to, I must say it's not that easy question. Okay, it's
Yeah,
not that
sure.
easy question. Yeah, and it could occur, but in my feeling that if you put too much light into the sample, maybe the sample should rather break or something like that. So it's a problem that I think it's a how to say, the matter of this lifetime of this excited state and versus this how to say, yeah. So if the
Yeah, I
lifetime is
understand.
very
Yeah.
long, yeah, I think you already understand. And
Yeah.
for my feeling in this particular ion selenide case, as I did the experiments, in my feeling, I think it's difficult in this case. Yes, but it's not trivial. Yeah.
Yeah, I see. I have another question, but maybe I'll let
Okay.
someone else ask, and if there's no questions, I'll ask.
Okay. If there is there any question?
Okay, so maybe I'll go ahead and ask the other question, if that's
you
fine.
can continue. Yeah.
So when you show that the Fermi surface loses its it's not isotropic anymore, so that's like the signature of the nematic phase, if I understand it correctly, that I have some elongation of the Fermi surface in one direction, and then it's correlated with this is like the indication of the nematic phase. But if I understand correctly, so if I have an elongation of one of the crystal axes, it must be either in the A, B, or C axis. And in nematic phase, I can have any angle in space I want. And here it's very limited to like 3 axes. So how is this still considered the nematic phase? Is my question clear?
So okay, so you are thinking about a 3-dimensional case. I mean, A, B, C axis. Okay, I think.
Yes, so what I learned from school, let's say, it's if you have a liquid crystal, some nematic phase, I have some rod, it can point in any direction it wants. But for crystal structures, I know that I can only elongate in the crystal axis, and it forms domains in different areas, and it's hard to just freely select a direction. So how is this still considered nematic, if that's a valid question?
It's actually, I think I think I got your question, but yeah, this system is a three-dimensional system, but actually in my talk, I'm kind of rather assuming this system as a two-dimensional. Okay, so this is a very quite two-dimensional system. So it's a very layered system, and the Fermi surface almost like a cylinder like this. So so I only think about this A and B axis. So when you when you elongate along the, I forgot which is which, but when you elongate along A axis, then the Fermi surface gets elongated along this KY axis. So we only thought about, considered the two-dimensional case. But so
I'm less concerned about the dimensionality and more about the fact that I can only point in certain directions, meaning the crystal axis. And I know, let's say for STO, let's say if I have tetragonal domains, there are some selection rules to what angles can form between domains of tetragonal domains pointing it in different directions. So it's just, it sounds like there are many constraints when I'm talking about crystals changing spatial symmetry as opposed to like classical liquid crystals. So I'm just trying to understand if this analogy to classic liquid crystal breaks down for crystals and it's a more complicated case.
It's a quite difficult question, but so you're talking about this analogy between this classical liquid crystal. Nematic phase. So in this ion selenide system, I mean ion-based superconductor system or community, maybe we define the nematic state when it becomes C2 from C4. Okay, so at the first stage it has a fourfold rotational symmetry, but at some point it becomes two-fold rotational symmetry. So, but from the first stage, we are only talking about this two-dimensional case. I think you are already aware of it, but when you consider the C-axis, when you consider, for example, AC plane, it's already two-fold symmetric at high temperature. Okay, so we are only looking at the part of the electronic structure. I think only AB plane or XY plane. So, am I answering your question? I don't know.
I think I'm getting like a general impression about about it. So maybe I'm thinking too much about the structure of the crystal and not the electronic properties, which.
I see. Yeah. So yes. Maybe that is true. So, in this topic, many of us, or most of us, are concentrating on the electronic states, not the crystal structure. So maybe that's the point. Yes.
Yeah, I see. Well, thank you very much.
Thank you for your question.
All right. Any other question? All right. So if I don't see any further questions, I wish to close. Oh, okay. Please go ahead. Who is asking question? No? All right. So if I don't see any further question, I want to close this lecture, and I wish to please join me to thank Professor Ishizaka. Thank you very much.
Thank
right.
you very much. Yeah.
Professor Ishizaka, thank you very much. Okay, let's close this lecture. Okay?
Thank you.